This video is going to look at how we can solve stoichiometry problems, both under standard conditions as well as non-standard conditions. When we are looking at stoichiometry problems and we are at standard conditions, we are able to relate two different quantities using the relationship we know about a mole of a gas at STP, that it is always going to be equivalent to 22.4 liters. When you are not at STP conditions, you will have to utilize the ideal gas law to be able to relate the two quantities. And the reason why you will need to do that is that we don't have a relationship for a mole of a gas at the different range of possibilities that do not exist other than at STP. So we can use our ideal gas law to calculate the amount of gas that is present, or we could use the ideal gas law once we know the moles of the gas that are being that have been made or been used to determine what its volume would be, or its pressure, or what temperature it's at. So when you're not under STP conditions, you're going to have to utilize your stoichiometry to relate the two quantities that are being investigated, but you're also going to have to use the ideal gas law in order to identify whatever quantity of the gas you want to learn. So here we only have one gas in this example. Calcium oxide, also known as quicklime, is made by decomposing thermally calcium carbonate, CaCO3, and we are told CO2 is also made through this decomposition. 3.25 grams of the calcium carbonate was decomposed, and we want to know what the volume is of the carbon dioxide gas made when it's at 5 degrees Celsius and 0.875 atmospheres. So the chemical reaction for this decomposition process is shown there. CaCO3 makes one CaO and one CO2. So this is a reaction that only has ones for coefficients. It's balanced to begin with. We want to find out about CO2, our gas, but we have only information about one of the two solids, the calcium carbonate. So if we assume that all that calcium carbonate got used, we should be able to determine stoichiometrically the mass or the quantity in moles of the carbon dioxide that was made. If we want to find the volume of our gas, and we know the pressure and temperature at which the gas was at, if we also know its moles, we should be able to use our ideal gas law to find volume. Again, you can't find volume directly through stoichiometry because you are not at STP. You are not at 0 degrees Celsius. You're not at 1 atmosphere. So I'm going to take those 3.25 grams of calcium carbonate and I'm going to relate that to carbon dioxide using my conversions. Grams of calcium carbonate, grams always gets its molar mass. You also need to include coefficients. I know this time they're 1, but I still like to include them just to make sure we don't forget. Moles always is defined as 1, and its coefficient for CO2 is also 1. So when we do our math, we get that 0.0325 moles of carbon dioxide were generated when 3.25 grams of calcium carbonate were decomposed. Now that we know the moles of our carbon dioxide and we know the pressure and temperature of our carbon dioxide, we should be able to use our ideal gas law to determine the volume. We have our moles, we have our constant, we have our temperature converted to Kelvin, and we have our pressure, 0.875. The atmospheres, the liters, the atmospheres, the kelvins, and the moles all cancel. And then when we do our math through and account for sig figs, we get that the volume of carbon dioxide that could be made was 0.847 liters. This time we have ammonia being made from nitrogen and hydrogen gases. Your equation is shown. N2 plus 3H2 makes 2 NH3s. Notice the coefficients are not the same in this particular reaction. We want to know how many grams of ammonia are made. So I'm not asking you to find a volume, I'm asking you to find a mass. You're at 10 degrees Celsius and 1.13 atmospheres. And we're doing this from 7.41 liters of hydrogen and more than enough nitrogen, excess nitrogen gases. If you have an excess of one of your two reactants, your limiting reactant will determine how much product you can make. So in this particular reaction, the hydrogen is limiting, and we're going to use that to determine our ammonia. Now, all of the quantities in our reaction are gases, but because we want to find out about the mass of ammonia, we are not going to go about doing that initially using our ideal gas law because we don't know the volume of the ammonia that was made. We do know the volume of the hydrogen, and we know the pressure and temperature of the conditions in which these two gases were placed. We can use the pressure, the temperature, and the volume of our hydrogen gas to calculate its moles. Once we know the moles of hydrogen, we should be able to determine the moles of our ammonia. We can relate those stoichiometrically using our coefficients from our balanced equation. And at that point, we still don't know the volume of the ammonia that was made, but we can convert from moles to grams. So we're going to use our ideal gas law first to find out about the quantity that we can find information out about given the material presented in this problem. We have the pressure of our gas, we have the volume of our gas, and we have our temperature. Once we account for all the units canceling and we solve through with our math, with 3 sig figs, we get that there were 0.361 moles of hydrogen that were consumed in this reaction. If that's the moles of hydrogen that were consumed, when we account for the stoichiometric ratio between the hydrogen and nitrogen, we can convert the moles of hydrogen into ammonia. Sorry, I think I said moles of hydrogen and nitrogen, moles of hydrogen and ammonia. And then we can use molar mass to convert those moles of ammonia into grams. So moles got the 1, grams got the molar mass of ammonia, the coefficients were placed, the moles of hydrogen cancel out, and 4.10 grams of ammonia were actually made as a result of this process. So the final piece of this, I ask you if you have how many liters of ammonia were made, and we're basing this off of the reaction we just talked about, so you still have that initial mass of ammonia, if the temperature and pressure were lowered to STP. So if we know the amount of ammonia we made and we have a new temperature and pressure, we should be able to, at this point, calculate our volume. We can do that using our ideal gas law, but because we are at STP, we can also use that relationship that 1 mole is equivalent to 22.4 liters, and that 1 mole is equal to that gas's molar mass. When we do our math through, we get that 5.39 liters of ammonia was actually present. If you had used the ideal gas law to solve for volume, we would have taken those grams of ammonia and converted them into moles, multiplied that by our constant and our Kelvin temperature, and divided all of that by our standard pressure. The atmospheres, the moles, and the Kelvin cancel. When we go through and do our math, we want to have 3 sig figs in our answer, and it's off by 1/100th. But whether you use STP or whether you use your ideal gas law, or I guess another possibility you could do in this particular problem, because the amount of gas was not changed, was that you could use, actually I don't think you could use combined gas law because you didn't know the initial volume. These were your two possibilities. So I hope that helps, and let me know if you have any questions.